Hello and welcome to the third part of our chemical energy storage session, where we talk about the charging technologies. And here we want to concentrate on what we can do with the hydrogen to produce other chemical energy carriers. And so why not stopping with hydrogen? First reason is that we don't have an existing infrastructure for hydrogen. And alternatives to pure hydrogen are methane that can be gained in a power-to-gas reaction, or power-to-liquids, or even power-to-chemicals that we can substitute oil products also in the chemical industry. The conversion methods that we have for hydrogen is the methanation, that can be chemical or biological. It's the methanol synthesis, or we can also mention as an example the Fischer-Tropsch synthesis. Whenever we want to convert the hydrogen to further hydrocarbons, so means a conversion from H2 to CmHn and multiples of that, then we need a carbon dioxide source. And when we look for CO2 sources, then we need to question ourselves, is it really a climate neutral resource? Because only then we can end up in a renewable energy system. Or it is just maybe something like greenwashing of coal industry, or what else? And then we need to question ourselves, is the application reasonable, or maybe is the energy expenditure too high for that CO2 source? And so then we come to some sources here in this table. We could have a biogenic CO2 source. That means what we get from biogas, it always contains CO2 that we can use, it's reasonable. Or we can have the CO2 recycling, meaning out of combustion processes when we combust bioenergy. Also that is a CO2 neutral way to gain the CO2 for our power to gas processes. And then we can use CO2 from the atmosphere. Clear, it is a climate neutral way to do it. But as we know, CO2 is in the atmosphere, but the proportions are quite small. We talk about of parts per million. So it's a quite difficult way to absorb the CO2 from the atmosphere. And then we have the CO2 from power plants, from the traditional industry, and then of course we have sources that is no longer climate neutral. When we go for the chemical methanation, there are two reactions. The first is the water-gas shift reaction, where we have the hydrogen plus the CO2 that reacts then to carbon monoxide and water. And we have the CO methanation, where we have 3 parts of water and carbon monoxide, and then that reacts to CH4, to natural gas and water. And the overall reaction is then 4 parts of water plus carbon dioxide reacts to natural gas methane plus 2 parts of water. The overall reaction is exothermal. The thermodynamic low temperatures and high pressures is meaningful. So we can make this process with all types, not all types, but with a high range of temperatures from 200 to 600 degrees Celsius, and with pressures from 20 to 80 bars, and with some catalysis. But we should not go below 200 degrees Celsius, because then the catalyst can be poisoned. But there we already see at temperatures like that, of 200 degrees Celsius and higher, we already have an excellently suited combined heat and power technology. So it's not only to produce methane, we also have heat that we might utilize in future. When we look for the methanol synthesis, so the power to liquids, and we look here for the methanol, the CH3OH, then we see which enormous range of products which can generate out of renewably generated electricity. We can use it as a pure fuel. We can mix it with gasoline or as a gasoline additive. We can produce formaldehyde out of it. Okay, that has not a good reputation, but it is needed for dyes in medicine to produce plastics, etc. Then we can produce DME. Again, we can add this to conventional diesel, but also we can use that to ethane and propane production. And then we also can substitute oil products in the plastics industry. Or where is it used? It's also used in acetic acids, in MTBE and other ways to substitute fossil energy carriers. The methanol synthesis, there we have mainly three procedures to produce methanol. And the first is the synthesis by the indirect conversion of methane to methanol. So there we have two reactions. The one is the partial oxidation, where we have the CH4 plus oxygen reacts to carbon monoxide and hydrogen. And we have an exothermic steam reformation, where we have the CH4 with water reacting to carbon monoxide. And then we have a common secondary reaction, where we use the generated carbon monoxide with the hydrogen we have produced, for example, in the electrolysis, and that then reacts to the methanol to CH3OH. And when we combine those two reactions in the right way, we also can manage to have an orthothermic reformation reaction. The second way is the synthesis by direct conversion of methane to methanol. And this synthesis is preferred because the generated synthesis gas production can be saved. To use pure oxygen here is better than air, because costs due to the pressure generation of 10 to 20 bar can be omitted, and a small part of formaldehyde can be generated, which can then lead together with methanol to the complete oxidation of the methane. And the third is then the renewable hydrogen together with carbon dioxide, and those two then directly can react to CH3OH plus water. And then ending here with an example of the Fischer-Tropsch synthesis. Here we have a polymerization process in which carbon monoxide and hydrogen can form hydrocarbons with various chain lengths. The synthesis gas production is by reverse water-gas shift reaction. And the basic reaction starts with carbon monoxide, so N parts CO, plus 2N parts hydrogen, then can generate different lengths or multiples of CH2 plus N times water. And when we now choose a certain catalyst with a certain combination of temperature and pressure, we can influence the product. So we have a reaction to produce mainly alcohols, or to produce mainly olefins, or to produce paraffins. And the probability of the composition of these products we see here in this table, depending from this factor alpha, we have either more gaseous products, the C1 to the C4, or more oil products, C5 to C10, and so on until to the voxes. And this alpha is the chain growth probability depending on the chain growth and the chain decomposition that can be influenced by choice of a catalyst. This here is just showing the result when we have an alpha of 0.85. Then we see on the very left we have a smaller fraction of gases that are produced. Then we have some oil products in the red bars, the diesel oils in the green bars, and the voxes and paraffins here in the violet bars. So that was a short overview on how we can generate from hydrogen gases, energy carriers that we can store, liquid energy carriers that we can store, and even substitute chemicals made of fossil fuels that we can substitute by renewable electricity. So to end up with this section, some questions. What are the advantages of chemical storages? What are the advantages and disadvantages of hydrogen as an energy storage? What conventional processes to produce hydrogen do you know? Explain the production of hydrogen via concentrated solar power. What does AEL, PEMEL, HTEL, SOEL mean? Explain these terms. Which CO2 sources exist? Evaluate these based on climate neutrality and sense. What means methanation? Which production methods exist? What are the production methods for power to liquid? What are the production methods for power to chemicals? So thank you very much for attention. Bye bye.